So hello everybody, welcome to this important series of constraint motion. So we are dealing with this fourth problem in the constraint motion series, and in the fourth problem we have a ring of mass m2 and a block of mass m1, and they are held in this position which is shown, and on being released, m2 being greater than m1 will start sliding in the downward direction on this vertical pole which is frictionless and perfectly smooth, and we need to establish a relation between the two systems, that if m1 is rising with a speed u and m2 is moving on this vertical pole with a speed v, what will be the relation between the two velocities. So over here, if we start the problem, we will be solving it using two methods. So let us begin with the longer method one, or the conventional method. So in the conventional method, let us redraw the diagram of the configuration which we have. So we can consider this one as the configuration where this is the distance d between the vertical pole and the fixed shaft. Over here, if I consider the original position of the ring to be this point, and the ring slides down by a distance y, while the distance of the block is x. So over here we can say that the total length of the string is constant. So over here originally also this distance was d, and if we consider this part or the length of the string L, then L plus d is a constant throughout the problem. So over here this is the logic which we are using, that L plus d is equal to constant throughout the problem. So over here, as x is getting diminished with the rise of u in the upward direction, we can say dx by dt is equal to u. And similarly with y moving in the downward direction, it will acquire a velocity v. So we are writing dy by dt is equal to v in magnitude. So this is the equation which we have. Now if we establish a relation that the length of the string is constant, so if the total length of the string is constant, then we can say that the distance x plus, we can say that this portion, that is root under y square plus d square, so this entire length must be a constant. So if we differentiate with respect to time, then we can say dx by dt plus half of root over y square plus d square multiplied by 2y dy by dt is equal to constant derivative with time is equal to 0. So this is the equation which we have, and if we solve this one, then we can say that dx by dt is equal to u plus 1 by 2 times of root over y square plus d square, which is equal to 2y, and dy by dt can be written as v over here, which we equate to 0. So over here we can say y upon root over y square plus d square. So if we write an equation for y upon root over y square plus d square in terms of theta, then we can say that cos theta is equal to y upon root under of y square plus d square, that is this portion can be written as cos theta. So therefore we can say u plus cos theta times v is equal to 0, and therefore v can be written as minus u upon cos theta. Now since over here we have already stated that we are just writing the magnitude aspect, so this is the answer which we can say in terms of magnitude, that magnitude of v is equal to magnitude of u upon cos theta. So this is the answer to this problem using the conventional method, where we say that the length of the string is constant and the separation between the vertical shaft and the point on the fixed pulley is constant. Now if we solve it using the method which we discussed while discussing problem 2, so in case you have skipped problem 2, kindly go back and watch that problem. It is very important and crucial. If you understand that, then it will become very easy for you to solve this problem in 2 steps. So let us do it using 2 steps. So at an instant of time, if we consider that tension in the string is T, so this is the tension T which we have. So it is rising up with a speed u, and this is falling down with a velocity v, and this is the angle theta which we are talking about. So over here, if we do the product of T and V, then we can say T times U for the entire problem, that is work done by the internal force, will be 0. So T into U in the forward direction, and T cos theta multiplied by V being in the downward direction is negative, and this is equal to 0 since work done by internal force is equal to 0. And from here we can just solve the problem in 2 steps, that T cos theta times V, and therefore from here we can say that V equals U upon cos theta. So in terms of magnitude, we have established this relation in less than 1 minute time. V equals U upon cos theta. So using this aspect is very important. This was method 2 and this one was method 1, where we used 3 or 4 equations to solve the problem, and then over here we can just solve it using the faster approach. So I am again repeating, in case you have skipped problem 2, kindly go back and watch problem 2. So this was the 4th problem in the constraint motion series. We will discuss the 5th problem in the next video. So continue to like, share and subscribe the channel for more such content.